Hi, hello, I'm Kiran Kumar from Nature of Physics and Art. Welcome to my channel. Now we will discuss electric field intensity or electric field strength and electric potential of a spherical shell or metal sphere or conducting sphere. Anyhow, meaning is same only. First, I will explain the electric field intensity based on the Gauss law, and second, electric potential V, that is based on the EVD relation. Okay, step by step we will discuss. Now, considering this is the spherical shell, uniformly positive charged spherical shell. So, and this upper sphere is taken as a Gaussian sphere, dotted lines. On the Gaussian sphere, surface area is S and small element area is ds, and ds bar is the area of vector, and electric field is radially outward direction, so this is the electric field is E bar. So here theta is equal to 0. Okay, and electric field E bar and ds bar, small element area, both are same direction, that's why theta is equal to 0. Okay, so for this, first I'm going to write surface charge density, surface charge density sigma. So sigma, which is equal to charge divided by area. Area of the spherical shell is 4 pi r square. Okay, that is capital R is the radius of the spherical shell and small r is the radius of the Gaussian sphere, and continuation here charge, enclosed charge Q, which is equal to 4 pi r square into sigma. Okay, and try to understand. Next one is Gauss law. Okay, according to the Gauss law, closed integral E bar dot ds bar is equal to Q by epsilon naught. Okay, so closed integral E into ds cos theta, but theta is equal to 0 here because of E bar and ds bar both are along the same direction, so we can write here theta is equal to 0 and cos 0 is equal to 1. So then we will get, which is equal to Q by epsilon naught. So E into integral ds, which is equal to Q divided by epsilon naught, and continuation E into integral ds is S, that is surface area of the Gaussian sphere is 4 pi small r square. Okay, which is equal to Q divided by epsilon naught. So here we got electric field intensity, that is outside. Okay, so that we can take the condition is here R is greater than to the capital R, that is the first condition here. Okay, so small r is the radius of the Gaussian sphere is greater than to the radius of the spherical shell, and that is taken as E out. E out is equal to 1 by 4 pi epsilon naught Q divided by R square, so that we can write it is E out, which is equal to kq divided by r square. So where k, which is equal to 1 divided by 4 pi epsilon naught. Try to understand. We got these two equations, and also we can replace in this equation charge, that is 4 pi r square into sigma. Then the resultant equation is here. Okay, so E out, which is equal to 1 by 4 pi epsilon naught. Okay, and the Q value is 4 pi capital R square sigma divided by small r square. 4 pi is get cancelled, so we got E out, which is equal to sigma divided by epsilon naught capital R square divided by small r square. This is the electric field intensity outside the spherical shell, that is small r is greater than to the capital R. We got the total three equations. So this is the first equation, E out is equal 1 by 4 pi epsilon q by r, and second equation kq by r square, and third equation sigma by epsilon naught capital R square divided by small r square. Then next we will discuss on the surface, and next inside the surface, step by step we will discuss. Just a second, I will clean the board. See now, continuation here, second condition, that electric field intensity on the surface of the spherical conductor. Okay, so for this small r is equal capital R, first condition already completed, that is outside, that is small r greater than to capital R, and q is the charge on the spherical shell. Okay, so for this we can write directly based on these equations, that is from first case, that is outside the spherical shell. So for this, E on, which is equal to small r is equal capital R, that is kq divided by capital R square. Instead of small r, I wrote the capital R. And next one is E on, second equation, sigma divided by epsilon naught only. Because of small r, capital R is get cancelled here. We got two equations here for the electric field intensity on the surface of the spherical shell. And next one is third one, that is inside the spherical shell. So small r is less than to this capital R, that is the Gaussian sphere is inside the spherical shell. Clearly I given to you diagram. Here we are assuming the small element, and this is the ds bar area vector, and this is the electric field, and both are along the same direction. Theta is equal 0 and cos 0 is equal to 1. And again we will get from the Gauss law, electric field intensity is equal to 0 because of inside there is no charge, that's why electric field intensity is 0. Just I wrote one step here. So according to the Gauss law, closed integral E ds cos 0, which is equal to q in divided by epsilon naught. So here we will get E into 4 pi r square q in divided by epsilon naught. So E in, which is equal to 1 by 4 pi epsilon naught q in divided by epsilon naught. So that is equal to 0. Reason is q in is 0, q in is equal to 0, 0 into anything, 0 by anything is 0. So we are getting here E in is equal to 0. So electric field intensity on the surface, and first one is outside the surface, and this is inside the spherical shell. Inside there is no electric field intensity, and we can draw the graph also here. The graph is like this. On the y-axis is considering electric field intensity, on the x-axis considering here R value. Okay, so now the graph is like this. This is small r is equal capital R, this is small r is equal to capital R. Okay, and here E outside, which is inversely proportional to the r square. See, from this equation, E out is inversely proportional to r square because of k constant and q also constant. So next to here, electric field intensity on. So this is E electric field intensity on. How much we got? That is kq by capital R square. That value we can find here. We can locate here. This is E on. Okay, so but E in is equal to 0. There is no electric field inside the spherical shell. This is the graph for the conducting sphere or matter sphere or spherical shell. This is electric field intensity. We did with the help of Gauss law. Okay, first one is outside, second one is on the surface, and third one is inside the surface. And based on the EVD relations, we can find the electric potential based on the three conditions. That is also potential outside the spherical shell and on the surface of the spherical shell and also inside the spherical shell. With the graph we can discuss. Just a second, I will clean the board. And continuation, now electric potential of a conducting sphere. For that I am using the EVD relation. We got already electric field intensity outside on the inside the spherical shell. So first condition is small r greater than to capital R. Here EVD relation dV, which is equal to minus E into dr, integration on both sides. For this continuation, integral dV is V, which is equal to minus of integral E value is kq divided by r square. K value is 1 by 4 pi epsilon naught into dr, here remaining value. Okay, so rearranging the equation, V out, which is equal to kq minus kq is common, and integral r to the power of minus 2 into dr. Okay, and the continuation value V out, which is equal to minus kq, that is r to the power of minus 2 plus 1 by minus 2 plus 1. This minus is get cancelled, so V out, which is equal to kq divided by r. We can write another equation, V out, which is equal to 1 by 4 pi epsilon naught q divided by r. This is the electric potential outside the spherical shell. Okay, and next one, second. So small r is equal to capital R, that is electric potential on the surface, which is equal to kq divided by capital R, just small r replacing with capital R. And next one is V on the surface, that is just k value replacing 1 by 4 pi epsilon naught q divided by capital R. Here instead of small r I wrote the capital R. And next third one is inside. So small r is less than to the capital R. Here E in value, which is equal to 0. So we can write EVD relation. So V, okay, so that E is equal dV by dr, then dV, which is equal to minus E into dr. Okay, so from this equation here dV, which is equal to E value is 0, 0 into anything is 0, so we will get here V, which is equal to constant. So differentiation of constant is 0, so that's why V is equal to constant. That value V in, which is equal to kq divided by capital R. Okay, whatever electric potential on the surface, that will be inside the spherical shell, that is kq by R only, or we can write V in, which is equal to 1 by 4 pi epsilon naught q divided by capital R. Okay, on the surface and inside the surface of spherical shell, potential is remains constant, nothing but same on the surface and inside also, but electric field intensity is 0 inside. So this is the electric potential of a metal sphere. Now we have to discuss the graph. Just a second, I will clean the board and explain the graph potential and radius. See now continuation, the graph between the potential and the r, small r. See, small r is the radius of the Gaussian sphere and V is the potential. So we got three conditions. First one is electric potential outside and on the surface and inside. So for first one is electric potential V out, which is inversely proportional to the r, that is hyperbola. Inversely proportional to r, inversely proportional to r. Okay, and this is potential on, so this is V on. So okay, So V in value is 1 by 4 pi epsilon naught q by r, and V on value also 1 by 4 pi epsilon naught q by r. So here potential is constant from inside to the on the surface of the spherical shell. Thank you.